Dear students, I welcome you for the today's lecture related to the understanding of the transfer function of the second order systems. Now there are different second order systems, that is, one is the manometer, then damped oscillator, pendulum, pneumatic control valve. These are the different second order systems in which the differential equation is of a second degree. That is why we call this as the second order systems. The dynamics of the system, which is represented by a second order differential equation, that is known as the second order control system. So we will study the transfer function for the second order system. The transfer function that will be the same, similar to that of a first order system. For first order system, it is 1 upon 1 plus tau s. For second order system, the transfer function is 1 upon tau square s square plus 2 phi tau s plus 1. So this is how this transfer function that is achieved. It is on the same way of similar to our first order systems, where you have to take the balance of that particular system, the force component balance. Now consider the manometer. All of you are knowing this manometer. Two limbs are there and which are connected with a U bend, and in that the liquid that is provided. Initially, both the limbs will have the same liquid. Initially, both the limbs will have a same liquid. That is, say for in this case, your limb height, the liquid in the limb will be same initially. But now you are going to apply the pressure P. Force P is applied from one end of the limb. What will happen? The fluid inside this limb that will move upward, and certain height that will be achieved in the second limb. So this is the right limb and the left limb. At time t equal to 0, the manometer that is at a steady state, but the pressure that has been applied, so that h is the height of the manometer fluid above the rest position. This is the h above the rest position. So the change observed will be 2 times h. Total change observed will be the 2 times h. One h is this and another h is this. So this is what the total change, that is nothing but the 2 times h. Then there are certain assumptions. One assumption is that the gas density is very small, and so that is neglected. Then the flow is laminar. The fluid which is moving through this is in a laminar, turbulence create nahi hua hai. And the forces favoring the direction of the motion, are taken as the positive, and the forces which are opposing this fluid motion are taken as the negative forces. So we will take a balance over this manometer. One is the force P applied, that is the applied force applied pressure that is force which is equal to pressure into the area. So force due to the applied pressure P in the left limb, that is P into A. Then second force, which is the gravitational force. The fluid tries to move in the downward direction, is because of its gravity. So pressure exerted because of the gravity is H rho G, whatever the liquid height that is there. So H rho G is the total pressure exerted by the gravitational pull. So the forces due to the manometer liquid in the right limb under the influence of gravity, that is 2 times H rho G into the A, because we have taken this H as 2H. So height is represented as 2H. Rho G, H rho G, that is 2H rho G is your pressure into the area. Then third factor is the force due to the friction. Force due to the friction between the manometer tube and the liquid in the manometer due to the motion of the liquid. So that is the delta HF is the frictional force into the cross-sectional area. So delta HF you have already studied in the fluid mechanics related to that. That is 4F L upon D into U square upon 2G, where F is the frictional force, L is the length, D is the diameter, U is the velocity through which it is moving. And this frictional force F, which is equal to 16 upon Re for the laminar flow, and where the Reynolds number is du rho upon mu. So this F that becomes equals to 16 mu upon du rho. So substituting delta H or simplifying this delta HF, the head loss. So substituting this value of F in this equation, you will get these terms. That is 4F 16 mu upon du rho L upon D into U square upon 2G. Now you have to simplify this, so that I am defining U as dH upon dt. U is the change in velocity with, so the distance traveled per unit time. dH is the distance and dt is your time. So change in the distance per unit time, that is nothing but your velocity. Distance traveled in a unit time. And this is the frictional force F, which is equal to the delta H into the A. So multiplied by the A. So this is the total frictional force exerted. Now this is having the negative sign because this is opposing the motion, opposing the flow of direction. Similarly, the gravitational force that is also opposing the flow of direction, the applied pressure के opposition में काम कर रहा है ये. So this is taken as the positive and these two are taken as the negative. So now the total forces exerted and the rate of change of momentum. This is nothing but the mass into acceleration. Rate of change of momentum, that is mass into acceleration. So mass, which is equal to the volume into density. This is your volume into the rho density. This is the mass. And acceleration is rate of change of velocity. Velocity we have defined as dH upon dt. So rate of change of velocity is d2h upon dt square. So acceleration of the fluid is d2h upon dt square. So by the Newton's law of motion, the sum of all the forces acting is equal to the rate of change of momentum. Sum of all the forces acting is equal to the rate of change of momentum. So the different forces, three different forces that is acting on the manometer is, one is the pressure force, second the gravitational force, and the third frictional force, which is equal to the rate of change of momentum. So dividing by 2a rho g for simplification and defining the term that is L upon 2g and 16 mu L d square rho g. So tau square is L upon 2g. This is what tau square is, L upon 2g, and it is tau square into d2h upon dt square. And second is the 2 phi tau, which is 16 mu L d square rho g. 16 mu L d square rho g is 2 phi into the tau. So after simplification, you will get this equation. Now P upon 2 rho g is represented as the xt. Now why this is? X is generally we are representing it as a input variable. Now in this case the input variable is your pressure, applied pressure. So this is the applied pressure, and what is the output? The change in the height. The applied pressure is the your input and change in the height is the output. So you must have a certain relationship between the input and the output, that is your transfer function. The Laplace transform of the output deviation variable to the Laplace transform of the input deviation variable. So output terminology is your height and the input terminology is your pressure, which is represented in terms of the xt. So xt, that is P upon 2 rho g. So taking the Laplace transform, inverse Laplace transform for this, you will get t square s square hs plus 2 phi tau s h of s plus h of s, which is equal to x of s. So collecting all the terms for the output and for the input. So you will get the transfer function as the output upon the input, which comes as 1 upon tau square s square plus 2 phi tau s plus 1, where tau, which is equal to L upon 2g, and phi is equal to 16 mu L upon d square rho g under root of 2g upon L. So this is the transfer function for the second order system. However, these constants that is related to the manometer, these constants are related to the manometer. These values of this constant is related to the manometer. You will have the different values for this tau and phi for the damped oscillator, for the pendulum, or for the control ball. So all these are having the different values, but your transfer function that will remain the same as the 1 upon tau square s square plus 2 pi tau s plus 1. Now the second example is the damped oscillator. Now what this damped oscillator is there? A certain mass of block of mass m, which is moving on the rolls, and it is attached to a dashpot and to a spring. So this spring and dashpot both are opposing the movement, forward movement, because I am applying the force F to this box which is having the mass m. So applied force is in the x direction, and opposing these forces, they are the your dashpot and your spring. Both are going to oppose this applied force. So we can take a force balance over that. So the applied force, which is the Ft, applied force, that is the Ft. Now the resistance because of the spring, that is force opposing by the spring, is minus k into y, where k is your spring constant and y is the displacement. Y is the displacement of the box at any time t equals to t. And what will happen for the dashpot? The force due to the friction in the dashpot, that is F, is the frictional force into the change in the distance upon the time. Force, the frictional force into dy upon dt. So the total net force acting on the box, that is your Ft applied force. The opposing forces are the spring force and your dashpot force. So this is the applied force, the spring force and the dashpot force. The two of them are negative, and this is going to be balanced by the rate of change of momentum of the box. That is nothing but mass into the acceleration, which is mass into d2y upon dt square. So you will take the balance over that now, the force balance. So you will get a force balance, that is the net force acting on the box, which is equal to the rate of change of momentum. The variables used in the above equation, which are okay, right? So dividing this by the k factor. So m upon k, f upon k and ft upon k. Now tau square, which is represented by m upon k, or tau, which is equal to the under root of m upon k. Then the 2 phi tau, which is equal to f upon k, and xt, which is equal to ft upon k. This is represented as tau, this is represented as 2 phi tau, and this is represented as the xt. So your equation that becomes, or simplified, to tau square d2y upon dt square plus 2 phi tau dy upon dt plus y, which is equal to the xt. Now taking the inverse Laplace transform for this and simplifying that, you will get the same transfer function gs, which is equal to the ys upon xs, which is equal to 1 upon tau square s square plus 2 phi tau s plus 1. So this is the transfer function for the second order system. The transfer function is same in both the cases. However, the value of the tau and value of the 2 phi tau, they are different for your pendulum and for your manometer and for your damped oscillator. So similarly also we will consider the third, that is related to the pendulum. A pendulum consists of a pendulum which is attached to the vertical fulcrum so that it is pivoted at this point. So the weight of the rod is assumed to be negligible. The weight of the rod that is assumed to be negligible. The extent of friction between the pivot and the fulcrum depends on the tightly the rod is provided. So the third example, that is related to the pendulum, and the force balance for this pendulum, that can be taken as the F, which is the applied force, So applied force which will be resisted by the gravitational force plus the movement in the x direction. So that is the resistance due to the pivot. This pivot, the connected joint, that is going to offer the resistance. So that is CL into the d theta upon dt. This is due to the force due to the friction between the pivot and the fulcrum. This is the force due to the friction between the pivot and the fulcrum. At this point, whatever the friction that is going to occur is represented as CL d theta upon dt. And the force due to the gravitational force, that is the mass into the gravity into the sine theta. Theta is the vertical angle between the fulcrum and the rod. So this is your generalized force balance. Then again, that is equal to the rate of change of momentum, which is equal to the mass into the acceleration due to theta upon dt square. So after simplification, you will get the transfer function as 1 upon tau square s square plus 2 pi tau s plus 1. In some books, it is the written as the tau, or some books it is written as the t, whatever it is there. But the equation is same, meaning is the same. So this is related to the three examples we have considered. Now we will see the different actions or whatever the effects that will be observed on this. One by one we will see the effects. The response. In the last class we have discussed the 4 different forcing functions, that is the step input, the ramp input, the impulse input, and the sinusoidal forcing function, and their response for the first order system. Now today we are going to discuss the response of the second order system for these different forcing functions. Now the second order system exhibits a wide range of response. This is something new in this case. That is the wide range of response, and that must be analyzed and understood. However, for the first order systems, it is dependent on only the single parameter, that is 1 upon t tau s, the टाइम फैक्टर, द टाइम कांस्टेंट फैक्टर, उसी के ऊपर फर्स्ट ऑर्डर सिस्टम का रिस्पॉन्स डिपेंडेंट है. बट इन दिस केस द रिस्पॉन्स विल डिपेंड ऑन tau as well as will depend on the phi. So depending on the values of this tau and phi, the response is going to vary. And that is why it becomes more and more critical for the second order system to analyze. So changes in the parameters of the second order system can change the form of the response. That is more concerned. So second order transfer function, this is our second order transfer function, 1 upon tau square s square plus 2 pi tau s plus 1. Now the tau is your time constant and phi is the damping parameter. Now this phi damping parameter will have the different values. May have the value of 0. That means it is undamped. That means it is undamped. Phi equals to 0. That is undamped. Then phi less than the 1, that is called the underdamped. Then phi that is equal to 1, that is called the critically damped. and phi that is greater than the 1, that is overdamped. So these are the 4 different conditions that is associated with the phi. Out of this, the phi equals to 0, that is mostly neglected, and the 3 becomes more important. That is phi less than 1, phi equals to 1, and phi greater than 1. That is the underdamped system, critically damped system, and overdamped system. Now the characteristics of this second order control system is represented by the damping parameter, and the response of this second order system depends on the value of the damping parameter and the time constant tau, and that is why you will get the different values or the complex analysis associated with the second order system. Then the roots of this system, what will be the roots? Roots are complex and unequal for the underdamped system. Roots of this equation, you have to simplify this equation for calculating the roots. That is, the roots are real and equal, and the roots for phi greater than 1, that is overdamped system, the real and unequal. That means 2 are unequal and 2 are real. And complex. Complex and real, equal and unequal roots are there. Now, step response of second order system for damping parameter phi less than 1, phi equals to 1, and phi greater than the 1. For this transfer function, we are having the excess value for the impulse transfer, that is 1 upon as, substituting that for the different values of this and obtaining, simplifying, taking inverse Laplace transform, you will get the yt. I am not going into the details of the derivation part. You can see the derivation from any of the book. Then these are your 3 different responses. We are more concerned about the response and its analysis, that is of more importance. Response and its analysis. So the first parameter, that is the phi less than the 1, which is having the transfer function yt, 1 minus 1 upon root of 1 minus phi square e raised to minus phi t tau sine of 1 root of 1 minus phi square into t upon tau plus tan inverse of root of 1 minus phi square upon phi. Then phi equals to 1 yt, which is equal to 1 minus e raised to minus t upon tau into bracket 1 plus t upon tau, and phi greater than 1. This is your equation. Now they are simplified so that the equation or graphical representation, that becomes yt, that is nothing but your output, and the t upon tau is the factor, time factor. So this t upon tau and the yt, that is your output. Yt is your output and the time t. The same graphs we have also discussed for the first order system. So response yt. Now if it is plotted like this, you will get the 3 different behavior depending on the values of the phi. For phi, the damping parameter less than the 1, it behaves sinusoidally, and slowly that sinusoidal waves that are going to decay. Then phi equals to 1, it is having a response without giving any sinusoidal, and phi greater than the 1, the response that becomes sluggish. रिस्पॉन्ड करने के लिए, सिस्टम को रिस्पॉन्ड करने के लिए ज्यादा टाइम लग रहा है. So that depends on the value of phi. So step response of second order control system, the nature of the response shows that the response is oscillatory for the underdamped system. Then the response of the critically damped system is non-oscillatory, and the response of the overdamped system, that is also non-oscillatory. but becomes this sluggish than the phi equals to 1. So therefore the values of the damping parameter increases, the response becomes less oscillatory and sluggish in nature for the control system. This is most important. The values of the damping parameter that increase हो रही है damping parameter की values phi less than 1, phi equals to 1, phi greater than the 1, the response becomes less oscillatory from oscillations to the non-oscillatory and to the non-oscillatory and sluggish. So this is for the response of the second order system for the step change. Then for the impulse impulse response of the second order system for the damping parameters phi less than 1, phi equals to 1 and phi greater than the 1. So these three equations you will get, and when they are plotted graphically, its behavior is like this. For phi less than 1, more oscillations they are observed. For phi equals to 1, the less oscillations they are observed, and phi greater than 1, there is no oscillation, slight oscillation only on the upper side. But for phi less than 1, the more oscillations are there. And phi equals to 1, the less oscillations are there. That difference is there. So the impulse response of the equation is oscillatory in nature for underdamped system and less oscillatory in nature for the critically damped system, and sluggish response for the phi greater than the 1. That is the behavior for the impulse response. The next is the sinusoidal response. This sinusoidal response yt at steady state, which is equal to a upon root of 1 minus omega tau square sub whole square plus 2 phi omega tau square into the sine omega t plus theta, where theta, which is equal to tan inverse of 2 phi omega tau upon 1 minus omega tau square. Now input to this case is xt, which is equal to a sine omega t input. This is what your input, and yt is the response equation. So input amplitude is your a and the output amplitude is your a upon root of 1 minus omega tau square sum whole square plus 2 phi omega tau square. So this is what the response of second order system that you will get. Then depending on this, the amplitude ratio, this is for amplitude A, the output amplitude of variation upon the input amplitude of variation, that is 1 upon root of 1 minus omega tau square sum whole square plus 2 pi omega tau. This is the amplitude ratio. Now the amplitude ratio for the second order system depending on the values of time constant and depending on the values of phi, that is phi and tau के ऊपर ये values dependent है, और for first order system it depends on only tau. So the amplitude ratio for the second order system may be greater or lesser than 1. These values may be greater or lesser than the 1. However, the values of the first order system is always less than the 1 because it is only dependent on the tau. Here the tau as well as phi that is going to depend. So depending on these two values, this value of amplitude ratio that can be less than 1 or that can be greater than 1. But the values associated with the first order system, they are always less than the 1. The amplitude ratio values for the first order system is always less than the 1, and you cannot define these values for the amplitude ratio for the second order system. It can be either the less than the 1 or can be greater than the 1. And the phase lag for the second order system, that is phi theta, which is equal to tan inverse of 2 pi omega tau upon 1 minus omega tau square. And for the first order system, theta, which is the tan inverse of minus omega tau. Then this is graphically represented as, or the when you plot this transfer function for the steady state values, sinusoidal response of the second order system, you will get such a behavior. This sinusoidal behavior, and it is going to decay after some time. This oscillation, they are going to decay because of this damping parameter. Now, this is the y minimum, or you can say the initial value, y minimum. Then the y ultimate, this is what you have targeted, you will reach to this value. And this is what the maximum value that you can obtain. So the C2 is defined as the y minimum and the y ultimate, the distance between the y ultimate and the y minimum. And C1 is defined as the y maximum minus the y ultimate. That is, C1 is the difference between the maximum and the ultimate values of the response. C1 is the maximum difference between the ultimate value and the y maximum. And C2 is the response between the y ultimate and the y minimum values. So the overshoot, that is depending on the damping parameter, and this is represented as the C1 upon C2, and which is equal to e raised to minus pi phi upon root of 1 minus phi square. This is called the overshoot. Then overshoot decreases with the increase in the value of damping parameter. This overshoot, that will decrease with the increase in the values of the damping parameter phi. The next terminology is the decay ratio. Decay ratio, it is the ratio of C3 upon C1, as it is the ratio of the values of C3 for C2 or the successive peaks. Now C3 is the, again, the y maximum and the y ultimate, but it is for the second peak. Because there is a damping parameter, there is a decrease in the oscillation. So C3 will have the different value and C1 will have the different value. So it's a ratio between the C3 and the C1. So C3 upon C1, that is called a decay ratio. And this decay ratio is defined as the overshoot square. This decay ratio, which is equal to the overshoot square. And overshoot is equal to e raised to minus pi phi upon root of 1 minus phi square. So it becomes, decay ratio becomes 2 times the overshoot. Overshoot square. The next terminology is the response time. It is the time needed for the response to reach within the plus minus 5% of its final steady state value. Final steady state value is nothing but your ultimate value. Final steady state value is nothing but your ultimate value. When it reaches to, when this response value reaches around the plus minus 5% of this ultimate value, this is plus minus 5% of this ultimate value, then we can say that it has attained, or it has the time needed for the response to reach within the plus minus 5% of its final steady state value, that is nothing but the ultimate value, and it is represented as the response time. The next terminology is the rise time. It is the time that is needed for the response to reach its final steady state value. To reach its final steady state value for the first time. That is what the difference between the response time and the rise time. Rise time, that is for the first time when it reaches to the ultimate value. First time जब ultimate value पहुंच रही है, that is the T rise. So this is the C2 value जब achieve होगी, that is your T rise value. So T rise, that is calculated as tau upon root of 1 minus phi square sine inverse of phi plus pi tau upon under root of 1 minus phi square. So this T rise, it measures the speed of a response, how fast you will get the response. And secondly, the smaller values of damping parameter phi, the farther the response of the underdamped control system. So for phi greater than 1, the lower values, lower and higher values of the phi T rise can be calculated. Then next is the period of oscillation. It is the time period to complete one cycle. Time required to complete the one cycle, that is the period of oscillation. To complete this one cycle, that is the period of oscillation, which is equal to 2 phi t tau upon 1 minus phi square, that is the times per cycle, where f is your frequency, cyclic frequency, which is 1 upon tau, and the cyclic frequency that is related with the radian frequency w, as w, which is equal to 2 pi f. Then the natural period of oscillation, the second order control system continuously oscillate and it is free for any damping. If the damping parameter that becomes 0, then this natural period of oscillation Tn is obtained by putting the phi value that is equal to the 0. So T that becomes 2 pi tau, that is your natural period of oscillation. That is called the natural cyclic frequency and natural radian frequency. So you can have the different systems there, and there is the transient response and the steady state response also. The transient response, that is initially whatever the response you will get, that is the transient response. Once it has attained to the plus minus 5% of the ultimate value or the final value, then it is called the steady state response. Initial response is the transient response or the dynamic, you can say. The final response is your steady state values.